Okay, Maxim, ready? We're 2 minutes late. Okay, guys. Welcome back to the afternoon where you're all coffeeed up. Our first speaker is Victoria Kostina from Caltech, and she'll take it.
Thanks, Lalita. I am very excited to highlight this joint work with Chang-Hui Lin, who was a student at Caltech and who is now at Kronos Research in Taiwan, and Babak Hasibi, who is a professor at Caltech. Training of large-scale machine learning models involves performing gradient descent or related iterative algorithms to minimize an objective function f. Gradient descent moves the iterate, the model parameter x, in the direction of steepest descent of function f. And here eta is a constant step size that is chosen beforehand. And it's important for optimal convergence to choose this step size judiciously, because if eta is too large, the iterates bounce around too much. If it's too small, then too many steps are required for convergence. In distributed training, the worker computes the gradients, and the server successively refines the model parameter and decides when to stop the distributed optimization based on the target accuracy or delay constraints. Exchanging high-dimensional gradients presents a real bottleneck in distributed optimization. This communication delay significantly slows down the overall training process. And for this reason, in recent years, there's been an explosion of interest in methods designed to alleviate this communication burden in exchanging these high-dimensional gradients. A large body of this work focuses on designing quantizers for stochastic gradient descent. Another line of this work focuses on gradient sparsification, where several significant components of each high-dimensional gradient are preserved and the rest are discarded. And the components that are preserved are communicated with infinite precision. And the proxy for rate in this line of work is the number of components that are preserved. I would like to highlight only very few works in this very large body of work. The work that really started it all was this 2014 paper, which made a striking observation that quantizing the gradient down to 1 bit per dimension, that is sending just the sign of the gradient and completely discarding its magnitude, results in almost no loss in empirical convergence. So this is a very important insight, because what it told people is that there is a massive space for improvement in terms of communication that is required in distributed optimization. So we do not need to send those entire high-dimensional gradients. There is a lot we can do by with compression. And so this led to all these other works that later studied analytical convergence guarantees for these kinds of problems, and proposed different variants for this algorithm. Another important idea in prior work that I would like to highlight is what they call error compensation or error feedback. And what it is, it's simply the idea that you shouldn't quantize the gradient directly. Instead, you should add back previous quantization errors. You should compensate previous quantization errors before quantizing the gradient. And and actually, it was the same paper. So the same paper that started that noticed that 1-bit quantization doesn't result in performance loss. That also noticed that we should compensate past quantization errors. And I should also notice. I should also note that a lot of prior work indeed focuses on characterizing the convergence of naive, of what we call in our paper naive quantization. So naive quantization would just directly quantize the gradient without doing any error compensation. And then, of course, follow-up works extended further deepened this idea of error compensation. But what I would like to note here is that the idea of error compensation actually in information theory literature dates back, is a classical idea known under as the name sigma delta modulation. Okay, another point I would like to make about the prior work is that some of these prior works, they provide an algorithm and they provide analytical performance guarantees for that algorithm. But convergence lower bounds, what we call converses, are very scarce. And that's why I thought it would be appropriate to mention these two papers that that stand out in that sense, because they do provide a converse. However, the converse is limited in the sense that they restrict the class of algorithms they focus on too much. They actually only focus on naive quantization. So they fix the input to the quantizer to be the gradient of the current iterate. Nevertheless, they do look at lower bounds, and so I thought it would be worth, this works would be worth mentioning. Okay, so what we do, we take an information-theoretic approach to the problem, and we provide the necessary and sufficient bit rate necessary to achieve a target convergence speed. So we provide both the converse result, which says that you cannot do better than a certain performance within a certain class of algorithms. And we also provide a scheme, an achievability result, which attains this bound with equality. I would like to set up the problem formally, and we fix the class of functions to be the following. So I denote it by f sub n, and these are standard assumptions in a lot of optimization literature. So we assume that f is L smooth, which is the definition is here, and we assume that it's mu strongly convex. An alternative way of thinking about this is that simply that f can be sandwiched between those two quadratic functions. Mu with the quadratic function is coefficient mu from below, and one with coefficient L from above. So in certain sense, it performs like a quadratic function. And we also make the standard assumption that the minimizer lives in a bounded set. Okay, so this is important because obviously once we cannot, in practice, we cannot guarantee that our functions are nice like this. And so it's a very interesting direction for future work to try to drop some of these assumptions. And in fact, that's a lot of present work is focused on in these directions. Yes.
Was that demonstrated on non-convex?
I don't believe it was non-convex. It was mostly experimental. They didn't provide analytical performance guarantees.
But was it done on like neural networks?
I think so. Yes. Yes. Other questions? Okay, so before speaking about what is the fundamental limits achievable with quantized gradient descent, let's recall some classical results about the vanilla gradient descent. The following result due to Pollack says that for any L smooth and mu strongly convex function f, unquantized gradient descent satisfies the following convergence guarantee. So the iterate at step t minus the true minimizer, taking the norm of that, is upper bounded by sigma raised to power t times the norm of the initial, the starting point minus the optimizer. So here's sigma. We refer to sigma as the contraction factor of gradient descent, right? So what the result says is that gradient descent converges exponentially fast with this factor. And this factor is between 0 and 1. And it depends on the condition number of f. So the larger the condition number, the worse the contraction factor is. Like worse means larger, okay? And what's interesting is that this bound is actually tight in the sense that there exists a worst case problem instance f such that we can attain equality in this in this result. So, okay, the question we ask is that what is the smallest, the best contraction factor achievable with R bits per iteration? And when we say R bits, we need to formally introduce the problem. What do we mean by R bits? What is the class? Or in what sense do we mean this? And we chose to consider the simplest possible quantizers. And one important thing about this work is that there is no randomness in it. Actually, there is randomness in one result. I'm going to point out how it comes in, but there is no randomness. Everything is worst case. So it's very simple in a sense, very elementary. So a quantizer, so without probability, what is a quantizer? A quantizer of dimension n and rate r is simply a function from some domain D to Rn, where such that the image of Q satisfies this condition. So there are 2 to the nr points that this function Q maps our domain to. And this is in high dimension and low dimension, a uniform scalar quantizer, for example, is an example of this. So quantization rate for us is simply the log of this number of the cardinality of the image of Q divided by n. And we can also talk about relevant quantities that measure the performance of such quantizers. The dynamic range of a quantizer Q is the radius of a ball, right? So here this blue region is our domain, and then the radius of the largest ball that can be inscribed inside of this domain is what we call dynamic range. This is just done to generalize the usual notion we're used to for scalar quantizers, the usual notion of dynamic range to multiple dimensions. Covering radius of quantizer Q is simply the radius of the smallest distortion ball with which that set of quantization points covers the entire space. Okay, so the covering radius, the quantizer Q with covering radius D is guaranteed to cover our domain up to distortion D. Okay, so everything is worst case. There is no probability here. And then covering it. And so how do we compare to different quantizers? Again, here we simply extend this classical notion of covering efficiency, which has been developed in the context of lattice quantizers to these quantizers with bounded domain. So covering efficiency is this quantity, and it's a quantity that's between 1 and so it's greater than or equal to 1, and 1 corresponds to a perfect covering with distortion d balls. What do I mean by perfect covering? If I could cover a set perfectly with n-dimensional balls without any overlap between them, this is what I would get. I would get covering efficiency of 1. But in practically implementable quantizers, this would be a quantity that is greater than 1. And for example, uniform scalar quantizer would achieve a covering efficiency of square root n. Right? So this is not the best quantizer, right? You can, in high dimension, you can find the better coverings. And a classical result of Rogers says that as n goes to infinity, the covering efficiency of arbitrarily close to 1 is achievable. Okay, and this is the only result that uses randomness in this talk, because to show this, he uses a random lattice construction. Okay, so naively, what is what we call naively quantized gradient descent? So this is a class of algorithms that has been extensively studied, and what it does, it simply quantizes the gradient directly. So it doesn't do anything else; it just quantizes the gradient, sends it back, and then the parameter server operates in exactly the same manner as it would have operated without the quantization. And so what we can do, we can analyze the performance of this algorithm, and we can show that the achievable contraction factor is bounded by this quantity, where sigma is the achievable contraction factor of unquantized gradient descent. And then you have this communication cost, right, which is a function of covering efficiency, rate, and also a function of condition number of the function f. So one thing to notice about this, as r goes to infinity, then we can recover the contraction factor of unquantized gradient descent. Another thing to be aware of is that this is not the best scheme, because what happens is that in the analysis is that these quantization errors, they accumulate iteration to iteration, and this results in this additive penalty term. Yeah, so we can actually do better than this, significantly better than this. And how do we do better? Well, we do better by relaxing this naive assumption that the quantizer should directly quantize the gradient, and instead we say, okay, the class of algorithms we're going to focus on is going to ask the worker to construct Zi, the gradient access point, and construct Ui, the quantizer input, based on the current iterate and the past quantization errors. Okay, so we give this additional freedom to the worker to decide what it is that it should send to the parameter server, so as to maximize the convergence speed in this context. Okay, so in a sense, it's context-aware communication. Right? So we want to really design our quantizer input to match this particular action that's happening at the parameter server. Okay, this is another constraint that we have here, is that the parameter server simply performs this update.
Very simple question. So if I was doing, maybe I know this is all gradient descent, so maybe I shouldn't ask this question, but stochastic gradient descent would create a noise, and if this threshold is smaller, I don't have to worry about this. I could get this. My quantization is fine, I suppose. I could get away with it.
I'm not sure I understand the question. We do not look at stochastic gradient descent. We look at the vanilla gradient descent, but there's been a lot of work. Actually, most work in this domain concerns quantizing stochastic gradient descent.
Okay, but I can see here, as you say, if I keep quantizing the variance, I'm creating this error in the update itself.
Yes, so my point is going to be that, yes, I'm creating exactly. So you can think of this as
that could be viewed as a stochastic. Even
yeah, actually that's the angle that a lot of previous analysis take. They look at this added quantization errors as noise. Like so it falls into this larger framework of a noisy stochastic gradient descent, and then they make some further assumptions about the quantization error. For example, they make assumptions that the quantizer is unbiased, and then they can show some performance guarantees.
Iterating for that.
Yes. And yeah, but we don't do any of that. There is no stochastic. Nothing stochastic is here. Other questions? Okay. Right. So we widen the optimization space by giving more freedom to the worker. And so what I'm going to claim next is that you can do much better than what naive quantization does. Okay, so this is just a formal definition for the worst case contraction factor achievable within by a quantized algorithm A. So informally, maybe just look here. So informally, what this means is that the iterates behave like this. So you have exponentially fast convergence, and we ignore the sub-exponential factors. And we want to characterize this quantity. And this is the main, the converse to the main result, which says that the contraction factor of any quantized gradient descent algorithm operating at r bits per problem dimension satisfies the following inequality. And so you can see on the right-hand side here, it's a maximum of the two quantities, the sigma, which is the contraction factor of unquantized gradient descent, and 2 to the minus r, which is the cost due to quantization. And the proof of this combines two converses. Right? So by reduction to unquantized gradient descent, we can claim that we cannot do anything better than what we can do with full information. And the second bound is simply the volume division argument. So it's the same argument that's used to show that the covering efficiency of any quantizer is lower bounded by 1. Okay, so it simply gives you 2 to the minus r here. So it's ridiculously simple. What's amazing about this is that we can actually achieve this. Okay, and how do we achieve this? We achieve this with the idea we call differential quantization. And what it does, the main idea behind this is that we should compensate. Right, so we should compensate the past quantization errors. And how should we compensate them? We should compensate them by directing. So in this picture, x0, x1, x2. This is the trajectory of the unquantized algorithm, and x0, x1 hat, x2 hat. This is the trajectory of the quantized algorithm. So what I do, every time I want to at every time instance I want to direct my trajectory back to the unquantized trajectory, and if I form my quantizer inputs in that way, then I would be able to attain that converse result that I showed. One curious observation here is that it's the same step size is optimal as the unquantized gradient descent. So originally we thought, okay, maybe a different step size would be better for a quantized algorithm, but in fact it's the exact same step size that attains the optimal contraction factor for gradient descent.
The average of the convergence and stochastic gradient descent has the same step size too. Because it depends on what kind of trick convergence you're looking at, right? I'll forget.
Okay, so yeah, well, what's important to note about this result is questions.
You go question.
Yes. So, is it true that depending on the rate, you will be either dominated by directing or just taking the normal basically the quantization is going to be negligible versus.
And you always do the same thing. You always do this. Like that's the algorithm. Like that's the algorithm. It doesn't depend on the rate. You always do this. Depending on your rate, you attain one of the two contraction factors. You attain either 2 to the minus r if your rate is too low, or you attain sigma if your rate is high enough.
Right. So I understand, but what I was trying to ask is that, so if the rate is too low, then it just does it just look like as if you're just directing towards the trajectory all the time, and then if the rate is too high, you're doing basically it's as if you just don't care and quantize, and the quantization error is not that much.
Yeah, so if my rate is high enough, what the result says, what the analysis of this algorithm says is that effectively I don't lose anything. And so that's what I was going to say next, right? There is a threshold. Like the amazing thing about this is that there is a threshold which is finite, right? So if your rate is greater than this finite threshold, then we don't lose anything with this quantization. As you are saying, we are always actually able to direct our trajectory back to the unquantized one. And if my rate is less than, again, this finite quantity, then I pay a penalty. So it's there is a sharp phase transition in the behavior of this algorithm, and we attain the converse exactly. Okay, proof sketch. Proof is also pretty simple. So we perform some induction. So the quantized and unquantized trajectories are related by this equality. And then we have two terms. The first term is convergence of gradient descent. And the second term, we choose the dynamic range of the quantizer carefully so that we can guarantee that we are always quantizing the quantization error up to distortion D. So basically, what we want to guarantee that the dynamic range that we chose is enough to cover the uncertainty about to cover the uncertainty about the quantization error. And this is some numerical results. So here we show, okay, convergence rate, this should be a contraction factor. Okay, so low is good, high is bad. And this is our data rate per dimension. The unquantized gradient descent achieves this line. And naive quantization achieves this green curve, and differential quantization achieves this red curve.
From the previous slide, so you're saying the dynamic range has to change per iteration?
Yes, we have to adjust. So there's a formula with which we, like there's a recurrence relation which governs how we should adjust the dynamic range.
But that's known ahead of time, or you have to do that on the fly?
That you can compute ahead of time.
Okay,
so yeah, based on the class of functions that you have. Yes.
So if you go back to your plot, is it your result seems to say that DQGD would have descent even at like very low rates, right? But it seems to have this convergence thing. Are the red lines at 1 some kind of artifact of plotting? Or?
Oh, this one, yeah. Here we clipped the convergence rate at 1. If it's greater than 1, then you cannot attain linear convergence rate.
But if I'm using 2 bits per dimension, what's your? Is it because of the row? Like why in your? You go back to your previous. I thought it was always for any r greater than 0, it would.
Any r greater than 0. So you are, let me see, what is.
I didn't understand what would the. Oh, okay.
Okay, that's the formula. So here, okay, so this is, I think what.
Yeah, that's what.
We were plotting it for uniform scalar quantizer. So there is a penalty for being practical, right? So we are not actually plotting it with optimal. Rogers quantizer, but we are plotting it as a uniform scalar quantizer. And yes, and you can do better than this by applying vector quantization. You can actually beat these curves. This ones are just for scalar quantized. So what you can see is that with differential quantization, actually the difference is massive, right, compared to naive quantization. You gain like what two bits per dimension easily, and that's per problem dimension, right? And dimension is large.
Okay, so I think I should conclude.
Right? So yeah, we tried this with other real world. So this was a Gaussian ensemble, and then we also tried it with a real world matrix and observed the same thing. And yeah, so that's the main result. And I just want to briefly mention a couple of extensions. I wanted to mention that we can also extend the same idea to gradient methods with momentum. So gradient methods with momentum, they leverage the memory of the past to further accelerate convergence. So we can apply the same idea. The idea is to direct the quantized trajectory towards the unquantized one to also show similar results for this class of algorithms. And we look at two accelerated algorithms, the accelerated gradient descent and heavy ball method, and for both of those methods, we can show that similar conclusions hold. And so the conclusion is, in all three cases, if there is a finite threshold, if rate is greater than this finite threshold, then the differentially quantized algorithm attains the contraction factor of the corresponding unquantized algorithm. Takeaways. So the optimal, so we looked at the optimal trade-off between convergence speed and bit rate. We formulated the problem as a worst case problem. And what we observed is that it pays to leverage memory, like so differential quantization is much better than naive quantization, which discards the memory about past quantization errors. And there is a lot of future directions where one can take this. For example, a very intriguing one, a very natural one is how do we do gradient descent over noisy channels? Perhaps there is a formulation where you have bounded noise, and we can ask what is the amount of noise that you can tolerate, and what is the trade-off between convergence speed and the noise in this channel. Also very interesting to relax the conditions on F and to extend this to multi-worker gradient descent, where the challenge is to figure out how each of the workers should compensate their own quantization errors. Because in multi-worker, you cannot really compute the unquantized, each worker cannot compute the unquantized trajectory. So this is and Converse still applies to this case. We don't know, there is a gap between achievability and Converse. So if anyone is interested, let's talk about this.
Setting up a question or two. Yes.
So I was wondering if you, just out of curiosity, have you tested the differential quantization method in a non-linear optimization problem? Something like that. I know you can't prove stuff, but just like to see how it works.
We only tested it on least squares problems. Yes, so no, not yet. But yeah, as you said, the analytical result hold. Sorry, hold for beyond quadratic functions.
Any other questions? Let's start.